Meow. Meow. Hello, and welcome to 15.1, Part 2, which is entitled The Doppler Shift. Now, the Doppler effect, what it is, it's an apparent change in the frequency of a wave caused by relative motion between the source of a wave and the observer. The apparent change in frequency. The frequency changes when there's relative motion between the source, whatever's giving it off, and the observer. Allow me to show you. Did you hear a shift in the frequency? Maybe listen to this train whistle. If you listen to this train whistle now, you'll hear the frequency change as it passes by. Did you hear it? If you listen to this next train, you'll hear it really well. Listen again. Well, there it was. The Doppler effect. Here's another one. Listen to how his tuning changes. He sounds really flat after he went by. Here's another one.
Hey, Sheldon, there's something I want to talk to you about before we go to the party.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. Meow. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
Not Peter Pan!
I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh gosh.
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Hi.
Hello.
So what are you supposed to be?
Me? I'll give you a hint. Meow.
A choo-choo train?
Close. Meow.
A brain damaged choo-choo train?
Meow.
I still don't get it.
I'm the Doppler effect.
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Why don't you just tell people you're one of the 7 dwarves?
Because I'm...
The Doppler effect. I've got an animation that kind of explains how this all works. It's based on the principle that waves travel a set speed in a medium. There's no way to make a wave go faster or slower. So what I've got here is I've got an object, and it can emit sound. Now, I'll take this object, and when it's standing still, you'll see that sound is emanating away from my object at a frequency of 2 waves every second, and it's going equally in all directions. If I take my microphone here, you'll hear it. And you can still hear it back here. It's just not as loud. Now watch what happens when I take this person and I move them. And I'm going to move them at probably 37% the speed of sound. And I'm going to pause it. And you'll notice, look in front of the observer, the waves have bunched up. That means that you have a higher frequency. If I was standing here listening to this, I'm going to get a higher frequency, and you'll see that I get a frequency of 3.17 waves a second. And if I was going behind it, I'd get a lower frequency because the waves have stretched out. The stretched meaning the distance between the peak to the next peak and pressure wave has gotten farther, which means a lower frequency. And when they're closer together, they're coming at you more frequent, so you get a lower frequency behind it, a higher frequency in front of it. So when this goes by, you'll hear high frequency as it approaches you, getting louder. As it goes by you, lower frequency. Now, when you go faster, it becomes more apparent. When I travel at 0.733, I'll change my direction here, you'll see that these waves bunch up quite a bit. I'm getting 7 waves a second. Now I'm getting 1.15 waves a second. And something unique happens when I travel exactly at the speed of sound, which is known as Mach 1. If you travel at the speed of sound, you're emitting sound at the exact same, and you're traveling at the same speed, so as this thing approaches me, I can't hear it because it's traveling the same speed as the sound is, until all of a sudden, I get all the sound all at once. And if I travel faster than the speed of sound, this is called going supersonic. If I travel below the speed of sound, we call that subsonic. You'll see something else happen. I'm actually outrunning the waves of sound, and we have what's called constructive interference along this leading edge right here, and this is what a sonic boom is. So I'll wait for my plane to come back the other side here. So here it's coming, I can't hear it. I'm underneath, I can't hear it. It's straight above me, I still can't hear it, and all of a sudden, boom, I get this pressure wave, everything adding up all at once. See if you can see this. This is some footage of jets breaking the sound barrier. This one doesn't have much sound, but it's got a really cool picture. That's compressing the water vapor inside the humidity in the air. The space shuttle, when it launches, there's a certain point where it breaks the sound barrier. See if you can figure out where it is. I don't think I went past it. Oh, it's getting close, I can tell. Watch for the vapor cone. Right there. See? Broke Mach 1 right there, that little vapor cone that you saw. Here it is again in slow motion. Boom. Right there. Here's a jet. It's not breaking the sound barrier, but you'll notice that you can't really hear it. Until it rips right by you. Here's another one.
Traveling towards us and over the speed of sound, the Tomcat will make a supersonic flyby.
And it's cool. You'll see this is a conic section that cone gets cut by the water. Did you hear it? Sonic boom. Look at it. Completely silent until it passes you. And then the wave reaches you all at once. Here's another one going overhead. This one, oh dang it. there was one over in Brazil that they stopped doing supersonic flybys because that pressure wave can break windows. Back in the 50s when they learned how to break the sound barrier, that's that pressure wave that hitting all at once, it would break all of your windows. And at an air show over in Brazil, they flew by a library, and the whole face of it was glass, and it broke every window in the front. And you see it, that Doppler effect, that's the faster you go, the narrower that cone gets. So I can go at Mach 2 here, and you'll see that cone starts to flatten out. And you can actually figure out how fast jets are going based on that cone. The Doppler effect, it's that apparent change in the frequency caused by relative motion. Now, relative motion doesn't necessarily mean that the thing is giving off. My object can be completely still, giving off sound, and if I the observer, am moving into it, I get a lot higher frequency, and if I go past it, I get a lower frequency. So as long as there's motion between one or the two of you, either the source is giving off is moving, or the emitter or the detector, so whatever's detecting that sound is moving. There has to be relative motion. If it's moving towards you, you get a higher frequency. If it's moving away from you, you get a lower frequency. There's an equation that deals with the Doppler effect. It says the frequency of the Doppler effect is equal to the frequency of the source divided by v, the speed of sound, or the velocity, minus the velocity of the detector over v minus the velocity of the source. So we've got an example problem here. It says a trumpet player sounds C above middle C, which is 524 hertz, while traveling in a convertible going this speed. So you're in a convertible. Playing a trumpet. This thing's moving at a speed of 24.6 meters per second. The cart's coming towards you. So here's you. You're listening for it, and it says, what frequency do you hear? I know that I'm going to hear a frequency higher than. So my guess, I'm guessing it's probably going to be something around maybe 550, something higher than 524. Let's figure it out. The frequency that I detect is the frequency of the source, which is 524 hertz. V stands for the velocity. That's going to be 343 meters per second, minus the velocity of the detector. I'm standing still, so I'm not moving. Again, 343. The velocity of the source, that thing's moving at 24.6. Now, what's important to note is that if I was moving to and I was moving towards it, this would be a negative velocity. So that would be 343 plus whatever my velocity is. It gets a little bit tricky when they both get moving. So I'm just going to run this through my calculator. And but again, another important thing to note is I want this number right here, I want it to go up. And if you look at this whole fraction here, this is going to be a number bigger than 1, because 343 divided by something that's bigger than smaller than that, it's going to be a number bigger than 1, so it's going to force that to go up. So I take my calculator, 524. This might so be 343 divided by another parentheses 343 minus 24.6. And I get 564 is the frequency that I detect. And that seems right? You know, remember we guessed at 550 and we're actually getting 564? That seems like it's well within the ballpark of what we're expecting. And I had mentioned before, when you go faster than the speed of sound, these are some terms that we use when we get going faster than the speed of sound. I got some speed slang here. Mach 1, that's 1 times the speed of sound. Mach 2 is 2 times the speed of sound. 343 at standard temperature and pressure. 686 Subsonic, when you go below 343, this is a picture of a subsonic plane. Supersonic, any speed over Mach 1. So if you go faster than the speed of sound, supersonic. Hypersonic, that's actually something that some planes are getting into now, where you go over Mach 5. That's 3,800 miles an hour. So that's just a little bit to know about some speed slang. Yeah. So the Doppler shift, the apparent change in frequency of a wave caused by relative motion. And you saw Sheldon doing that. Things move towards you, higher frequency. Things move away from you, lower frequency.